So without wasting time, so thank you once again for joining this introductory statistics session. So for those who don't know me, my name is Clement Chumasi. So basically, I had my PhD in mathematics at Cardiff University, and from there I went further to do my postdoc at the Oxford Statistics Department, and then proceeded to becoming a clinical trial statistician at Imperial College, and later have joined the Nuffield Department of Medicine as a medical statistician. So I'm very, very humbled to be part of the team. And then, so without wasting time, I'll just recap the outline of the presentation. So basically, we are going to recap a bit about some of the upcoming STAS teaching sessions. Of course, at the end of this particular meeting, there will be a small survey that will be sent for researchers and also for everyone to give their feedback as to what else they want in terms of some specific needs of interest, so that we can cover in some future time. And so I'll also touch a bit on some useful information about variable types and data structures and how relevant they are when it comes to trying to test even hypotheses or also trying to do statistical analysis. And I also understand that we have different levels of expertise. So in a sense, some are new to statistical analysis or statistics in general, and some are advanced users and so on. So I'm hoping to try and get an intersection of the two. So at the end of the day, I'm sure everyone will pick something new or something useful for their respective studies. And so we'll touch a bit about univariate and multivariate methods in the context of both parametric and non-parametric cases. And then most importantly, we'll talk about regression analysis, since it's often one of the most sought after kind of statistical tests for across different disciplines. And then we'll touch a bit about variable selection techniques and what are some of the statistical softwares available that one could use to perform statistical analysis, and also even sample size determinations and so on. So I just touch a bit on a few which could be useful, and then we'll introduce a bit of about the next meeting that is happening next week, and then what we expect to see. We'll touch a bit on that as well. So as I said earlier, so on Tuesday we had a first STAR session, and we had quite a number of people joining. But unfortunately, since it wasn't recorded, I'm hoping to record this one because the previous one didn't have recording right. And so today is just a repetition of the first session. So it means next week, Tuesday, we are going to now introduce the second session of the introductory statistics session. And then there will be a repetition again on the Friday. And subsequently, the goal is also now trying to get researchers to present maybe the statistics bit of their work, and to get to get opinions as to the best thing they could do, or in case maybe they have a particular hypothesis, they have a particular data, they are not too sure what can be done in order to answer some specific research questions. So the goal was to have such an instance where researchers could now brainstorm over a presenter's work. So it could be maybe 3 people presenting within a certain period, maybe within a period of 1 hour, 30 minutes, and so on. But it's still something under the developing stage. So and it's also subjected to opinions, and also we are happy to take feedbacks as well. And then there was also plans of having a drop-in session where again, if anyone has a query, a statistical query, and they could book for such a session, and then we'll take it from there. But again, it's still something that we need feedback as to how we can do that to really optimize time, and also looking at the fact that we have researchers across different disciplines within the Department of Medicine. So for the introductory statistics session 1 is basically just trying to talk about like the basic or the most important things you need to know in statistics, just the basics. But of course, there will be something new you learn. And then in the session 2, we'll touch a bit on more customized statistical applications or more advanced methods that one could also effectively adopt in their respective analysis. options. But again, at any point in time where multivariate method becomes an option, always go for that, because in that case, you don't have any issues about effect of multiple testing. Somehow it improves power. And also think about degrees of freedom. I'm sure you've heard of degrees of freedom. Now, if you think about degrees of freedom in this way, if you have a model, if you have a statistical model, it's not always that you are interested in estimating all the parameters. So there are instances you are just interested in estimating a subset of the parameters. So if you look at the difference between the total parameters that the model can possibly have, and you take away the parameters that you want to estimate from that pool of parameters, that difference is like the degrees of freedom. So the degree of freedom is like those other parameters that is virtually not going to be touched, right? So if you do lots of univariate methods, it means that you tend to overestimate parameters, whereas in the multivariate case, you control for not having to estimate a lot of these parameters. So somehow it also conserves your degrees of freedom as well, depending on what you are trying to do. Okay, so this now brings us to, so the first part I just talked on was just summarizing basically the difference between univariate methods and multivariate methods and so on, and the fact that we've already touched on different data structures. So now we are going to learn how, if a data is cross-sectional or if a data is longitudinal, how does it really affect us and so on. So we are going to now look at it. So now we are going to introduce regression. But keep in mind, now we are talking about a linear regression. A linear regression means that anytime you are using a linear regression model, you are assuming that the predictors, okay, have a linear relationship with the outcome. And then there's other assumption that among the predictors, there shouldn't be high correlation among the predictors. And that is what we mean by multicollinearity. Multicollinearity is when we have high correlation among some of the predictor variables. And of course, you can easily see that descriptively, even from a correlation plot, to check if there's high correlation among some of the predictors or not. And when you have such an instance, later I'll tell you the effect of multicollinearity on your analysis. So, and then there's a particular assumption I want us to touch on is about the residuals. So when we talk about the residuals, it means that in a regression, you have your observed dependent outcome, and you are trying to predict for that outcome. So the difference between the observed and the predicted outcome is what we mean by residuals. And we expect the residuals to be normally distributed. And also we expect the residuals to be independent and identically distributed. The independence is not often achieved because often the residuals should sum up to 0. So somehow there's some independence there. But I think the most important bit is that the variance of the residuals should be constant. So meaning that independent and identically distributed, and it should be constant variance. So these are residual plots that could be used to test for some of these assumptions. That is visually. Of course, you could do proper hypothesis testing to check for that. So the normal Kekel plot is just a visual way of testing for normality. And so here, I mean, this is just a simple simulation that I did just to explain this bit. So here, this is the bit that I'm interested in, the residual versus fitted. So if you look at this red line, if this red line was fairly linear, then it tells that indeed there was a linear relationship between your predictors and on the outcome, which is what you are trying to check. And sometimes when you see a quadratic pattern, it might even suggest the reason why you need to now have a quadratic regression model rather than a linear regression. So there are instances you might see a polynomial pattern and so on and so forth. So I'm just trying to say that these are just ways of testing for some of the assumptions. And this particular scale location plot also tests for heteroscedastic and or homoscedastic, whether there's constant variance or not. And so here, often we want to see a fairly linear or horizontal line. And once it's fairly, this is not too bad, but once it's fairly, once it's fairly linear, then we can also conclude. But there are proper statistical tests for that. But here, the take-home message is that if you're trying to use a linear regression model, specifically a parametric linear regression model, there are specific assumptions. Don't just use it without testing some of these assumptions, because once some of these assumptions are violated, your effect sizes, your estimated effect sizes could be misleading and so on. But situations where some of these assumptions are violated, what people tend to do is that we try to do some transformation to the outcome variable. So here I just decided to introduce a few of or some examples of transformation people could do. So this is just based on a simulation I did. So let's say I simulated a certain data set at baseline and also after 3 months. So here I tried, so there's the original score, like the original, so there's a KQ plot trying to ascertain normality. Of course, there are parametric, there's actual test to test for normality, like using the Shapiro-Wilk test, Shapiro-Francia, Skinner-Sketosis test, and so on, and the Sunderland test, and so on. But here, I'm just using a visual way to ascertain. But of course, there's a p-value of a Shapiro-Wilk analysis there. All right, so here you can clearly see, look at the original score at 3 months in terms of the normality. And then if you look at that of, so this is called zero skewness log transform. Of course, we have log transformation, but log transformation only reduces the variability in the data and still keeps the structure. But zero skewness log transformation is trying to achieve what log transforms will do, but at the same time trying to set the skewness to 0. So it means a data could still be log transformed, but still would be skewed in any way. So most of the times people transform data sets and then try to see if it will preserve some of these assumptions of parametric assumptions of linear models. But here I'm going to touch a bit on some of the limitations of trying to over transform your data. So if you think about it here, I just did a scatter plot of the original score at baseline and at 3 months, and this is the original data. So it means in the original data we expected to see an increasing relationship between the two, a positive relationship between the two. But you realize that after transforming it with, let's say, the zero skewness log transform, it has now reversed the whole pattern. So this is to say that situations where a data is these parametric assumptions are being violated, why do we still want to force to still use parametric methods whilst a non-parametric version of this same thing, which will achieve the same results, will be imperative? So I'm just trying to emphasize that though transformation can sometimes help to preserve some of these assumptions under the case of a classical, in the case of parametric regression, where the parametric regression are basically trying to predict the means. But is it always the case that we need to predict the means, even in the presence of departure from these assumptions? And trying to transform the data sometimes can affect interpretability. And this is basically what I decided to achieve with this plot. So here, the 1R was not really sufficient for us. So previously we finished within 1 hour 30 minutes. So if I'm almost done. So if you could spare me 15 to 20 minutes so that I'll wrap up, because this is the most important bit. So I've already touched on some of the assumptions of regression. So here we have something called generalized linear models. So keep in mind that if a data is cross-sectional, then the class of models you could use are called fixed effect regression models. And if a data is longitudinal in nature or panel, that is, if the data was cross-sectional collected over time, and you still want to do the same set of regression analysis, then you now have to use something you call a mixed effect model. So it means that what's the difference between the fixed effect and the mixed effect? The main difference is about the fact that one is cross-sectional and the other, the fact that the data is longitudinal, predominantly longitudinal in space or time, or based on other metric, structural metrics. So basically for longitudinal data, others, that is for mixed effect models, others also call it multi-level models. But here I'll just touch on the cross-sectional case. So it means that for a generalized linear model, situations where the data is cross-sectional, and then you are trying to now use an OLS regression. That is what I just explained up there, where you are trying to predict the means of a certain single outcome, and then you are trying to ascertain those parametric assumptions are met. But if you look at just the residual, for instance, just the residual, you realize that we said for OLS, we expect the residuals to be independent and identically distributed, and the variance must be constant. By constant, in this case, it means if you look at each row of the data, we expect that the residuals in the outcome, we expect that the variance should be constant, meaning it shouldn't change. but it rarely happens in real life. So when it happens, then we use something called weighted least square. So weighted least square is when the constant variance assumption is violated, and then you now assume that the variance changes or is not constant from one subject to the other. And then keep in mind that here the assumption of independence means that there's no correlation or autocorrelation between the residuals. So with the weighted least square, it's also assumed there's also no correlation, but just that the variance are varying or changing. So that is where so it means that when there are departures of parametric assumption for the OLS regression, weighted least square could also solve the problem even without transforming. However, situations where there's also, apart from the fact that the variance changes, but also there's correlation between them, then the generalized least square, which is a natural extension of both the OLS and the weighted least square, becomes imperative. But keep in mind, these three are used when we are assuming that the outcome variable is continuous. But what if the outcome variable is categorical? Then it introduces us to class of regression model called logistic regression. So anytime you hear logistic regression, it means that the outcome variable or the dependent variable is categorical in nature. If the categories or the levels of the categories are just 2, then we have a binomial or a binary regression. And if it's more than 2, we have multinomial. And even with that, if there's ordering in the categories, it can introduce us to another class of logistic models called ordinal logistic, and so on and so forth. And then Poisson regression or Poisson class of regression models are situations where the dependent variable is discrete in nature. By discrete means that it cannot take fractional values. So if you are trying to predict for the number of, let's say, road accidents, if you are looking at the number of number of maybe genes, number of anything, then in that case the outcome variable is what is discrete. And in that case we use Poisson type models for analyzing such data, where you are trying to look at the effect of some predictors on that outcome, which is discrete or count in nature. But with the Poisson tool, there are specific assumptions that the mean and the conditional mean and the variance must be equal. That is in terms of the outcome variable. But when that is violated, quasi-Poisson and negative binomial, which if the mean and the variance are not equal, in the case of Poisson, then we say there's a dispersion in the data. And if the data could either be under dispersed, that is if the variance is less than the mean, or over dispersed if the variance is greater than the mean. And negative binomial and quasi-Poisson are used to solve that. But again, all what I just mentioned can be used for the case where we now have a longitudinal data. So it means all the models I've mentioned, both the logistic, the Poisson class, and so on, we can have the same class of models for the situations where the data is longitudinal. So for the longitudinal case, what happens is that, let's say you have the cross-sectional data that you have collected over time and space. So what we do is that it means that the data is hierarchical in nature. By hierarchy means that, first of all, there's pseudo replication in time and there's also replication in space. So what we do is that time and space, in this case, or situations where it's just collected over time, what happens is that time in this case was not of interest to you. If it is a fixed effect variable. So fixed effect variables are those predictors of interest that you want to see how they affect or predict the outcome. But situations where you have the predictors of interest, which are still your fixed effect, but there are other variables that introduces hierarchical structure to your data. Those variables are going to be put in your model as random effect. So it means for longitudinal data, where I said you are going to use a mixed effect model. Mixed effect model simply combines your fixed effect with random effect variables. But so the random effect variables are those variables that introduces some hierarchical structure to your data, but they are not of interest. But it's in the case of trying to use a regression, you need to account for the structure of the data. And there are also instances where you have different patients, and those patients are highly variable. So meaning that variability among the patients are enormous. This is to say that there are individual heterogeneity in your data. So in that case, you can also add patient ID as a random effect in the model to account for individual heterogeneity. So that is also another thing we have to know. So it means that for generalized linear mixed model, we are basically using the same class of fixed effect models, but this time around trying to account for temporal and spatial pseudo replication if they exist, or even account for individual heterogeneity in your data. But keep in mind, for these class of models, if it assumes that if you have a continuous predictor, there must be a linear relationship with the outcome variable. But in most cases, that is not often seen, even after doing a simple scatter plot. So situations where some continuous predictors have nonlinear relationship with the outcome, people can use polynomial regression to solve that problem. Like it could be quadratic or it could be something. However, one could still use a linear model, but what we do is that we try to use something called spline functions to smoothen out the nonlinearity in those continuous predictors that are nonlinear with the outcome. We try to use spline functions to smoothen out those nonlinearity. And that introduces us to another class of model called generalized additive models. So it means all the models I've mentioned, okay, when you try to now control or account for nonlinearity with some of the outcomes, with some of the predictors on the outcome, that introduces us to something called additive models. So we could also have fixed additive models and mixed additive models in the same fashion that I've explained above. And we have other class of models called machine learning techniques, which could be used for classification and also regression problems. But its use is very, very varying. So we could have machine learning to detect even facial recognition, voice recognition, and so on. But in terms of regression, the class of models, we have classification tree, random forest, and gradient boosting machines, and so on. The beauty about these machine learning algorithms is that it kind of summarizes your model in a tree structure. And sometimes researchers in sciences, or let's say in biology or in medicine, can sometimes appreciate some of these outcomes when you have your model fitted as a tree in a more unsupervised or supervised fashion. And that's what the machine learning does. One thing that I want to really touch on, which most people hardly use, is quantile regression. So remember that I told you, I made mention about the fact that all the linear models I've mentioned up here are trying to predict the means. But when their departure of first of all, if even your outcome variable is not normally distributed, in that case, there's a chance that your residual will not be normally distributed. So it means that predicting the means is not always desirable if you can predict the medians. So quantile regression is a way of trying to predict other quantiles of your data and not just the mean. So it means situations where you are interested in predicting the median, or predicting, let's say, the 25th percentile of your data, or sometimes you are doing an analysis. You've already used a linear model that is trying to predict the means, but you want to do sensitivity analysis to see if indeed the same factors that you were able to find to be significant on the outcome, would they still be significant if we're looking at other quantiles of your data? So that is to say that if we're looking at the median, or you were looking at the 25th percentile, or you are looking at even the maximum data point, or you are looking at different quantiles of your data, would we still see such consistency? So quantile regression is a more robust way of rather predicting not just the median. If we predict the median, then we have median regression. So if you've heard of median regression, it's just a quantile regression where the quantile is 0.5, basically trying to predict the means. So at the next plot, so there's a comparative plot where I decided to compare, I just used a simulation to compare quantile regression with the classical mean type regression models, and then we'll see the difference. So variable selection is very important, especially in situations where you have so many predictors and you're not too sure which set or subset of predictors should you use in trying to predict the outcome variable. So in that case, we now use a class of some methods to select those variables. So again, that's why I said in principal component analysis is rather reducing the dimension of the data. So people sometimes confuse principal component analysis for variable selection. It's not the case. So it means that stepwise regression is one method of trying to do variable selection. So what people do is that they put all the predictors in the model, and after fitting the model, they now try to identify a subset of that fitted model that will have the highest predictive power. In essence, that will have the minimum AIC or BIC. And then we have class of models called penalized regression. Apart from the fact that these penalized regression models can be used for variable selection, they can also help control for the effect of multicollinearity. So here I said be aware of the effect of multicollinearity. Multicollinearity is, as I said, is when we have high correlation among the predictors, which is not desirable. What are the effects of multicollinearity? You realize that when you fit a regression model and the overall model is significant, what that means is that at least one of your predictors was significant. If none of your predictors is significant, we expect the overall model not to be significant. But in the presence of multicollinearity, you realize that the overall model can be significant, but none of your predictors was significant, or vice versa. And then, so in essence, when multicollinearity is present, your regression, your results could be completely misleading. But when there's multicollinearity or high correlation among your predictors, one could use penalized regression methods to control for that. So it means that the penalized regression methods I've highlighted here, ridge, lasso, and elastic net, are suited to situations where you're trying to do a regression, a linear regression, but there are high correlation among the predictors. But what the ridge regression does, it doesn't do any form of variable selection per se. But what it does to control for multicollinearity is that those predictors that are less influential, or those predictors that are not relevant compared to the others, other predictors, it sets their effect sizes to a value very close to zero, meaning that the coefficient or the effect size will represent the weight. So what it does is that it sets the weight or the effect sizes to something very small, but not equal to zero. So, and if it was equal to zero, then it will reduce the dimension of your model, isn't it? But that is what we mean by the L2 regularization. What it does is that it minimizes those variables that are less influential or less important to have an effect size that is close to zero, and increases the effect sizes of those that are more important. But in the case of a lasso regression or the L1 regularization, what it does is that all those predictors that are less influential, it sets its regression coefficient to zero. By setting it to zero, it even tells you that those variables are not relevant, so take them out of your model. And that is why lasso regression is a perfect way of also doing variable selection. But ridge does not do variable selection, but just minimizes the influence of those variables that are less important. And then elastic net combines the power, or combines ridge and lasso regression. And so that is sometimes relatively more robust. Partial least square regression is also a type of penalized regression, also in the presence of multicollinearity. And then supercollinearity, which I'm going to touch a bit on. These methods can really help. Recursive feature selection techniques are also variable selection techniques. And we have machine learning type selection techniques like simulated annealing method, we have Burrito method, and so on and so forth. So there are other ways of also doing variable selection in the case of what? In the case of regression, that is when you have multiple or several predictors and you're not too sure which subsets should be considered in order to have a good predictive model. But one thing we have to notice is that in clinical trials, often we know the kind of predictors we are interested in. So it means variable selection techniques or variable selection does not apply to clinical trials. It often applies to observational studies where you routinely collected data or some health data with several predictors and you're not too sure which subset you should consider. But meaning that if you want to minimize the use of variable selection, you often need to know or have insight from clinicians to know whether indeed which predictors are of interest to them. But it is only when we are not too sure that we now try to use statistical approaches to do that. Supercollinearity, which I'm sure not everyone knows about it, is situations where you have a data where the number of predictors outweighs or are higher or is higher than the sample size. In most cases, we expect that the sample size is often larger. So by sample size, in this case, I'm talking about, in the case of a cross-sectional data, I'm talking about the number of rows of your data. So we expect the number of rows to be more than the columns. More often, so if the variables or the predictors are at the column section, and then the predictors or the columns are rather higher than the number of the rows. In this case, it's what we mean by supercollinearity. So supercollinearity it occurs when we have more predictors or more, basically more independent variables than the sample size. And what that implies is that it affects or introduces convergence issues. So if I'm sure most of us in the OLS regression, if you want to know the exact form of the least square estimator, the least square estimator has a component which is a matrix with an inverse. So situations where you are trying to find the inverse of a matrix and it's not invertible, meaning that it can't be found due to singularity issues. This is often sometimes attributed to these supercollinearity issues. So it means that apart from the fact that there are other contributions to having such low rank matrices or such invertible issues, supercollinearity is also one contributory factor. So, but when there are more predictors than the sample size, some of these penalized regression can still handle them. Okay, so that's basically what I wanted to. So I'm almost done. So this is just a graph. So this is based on a simulation study. So here, if you remember, there was this score that I produced. It's a difficulty score at baseline and at 3 months. And then so here we're trying to look at trying to predict the score at 3 months and trying to check its difference across some treatment. So we have a placebo, and then we have an active arm and a placebo in this case. So here what we decided to do was now to compare 3 types of model. So we now fitted I fitted a parametric ANCOVA. So remember, ANCOVA is when we are trying to look at how a certain outcome variable varies between some categorical variables whilst adjusting for the effect of other variables. So in this case, we're adjusting for the effect of the baseline score in the model. So, and then again, ANCOVA expects at least one of the outcome variable to co-vary with the one of the predictors, continuous predictors, to co-vary with the outcome. So in this case, even if you don't have such a case, you can still adopt ANCOVA. But in this case, the baseline scores were adjusted for as a predictor. Okay, so here we use the parametric ANCOVA and a non-parametric ANCOVA. Non-parametric ANCOVA, what it does is that it's just the method of estimation that will vary. So it means the interpretation will be similar, but the only difference is that whilst the parametric ANCOVA is trying to use least square estimation techniques, the non-parametric, which try to minimize the mean of the residuals, the non-parametric ANCOVA will be minimizing medians. So the function it will be minimizing is a median function rather than trying to minimize the mean of the residual. So basically that's what the non-parametric ANCOVA does. And then we compare that to a quantile regression where we're trying to predict the median. So here the red line represents the fitted median regression line, which is a quantile regression where the outcome variable is the 50th percentile or the median. And then if you look at this lower bit, the blue color, I don't know whether it's a violet color, is representing the rank-based ANCOVA, that is the non-parametric ANCOVA, and then the green one is the parametric ANCOVA in this case. And you can see there's no much variation, but somehow the rank-based ANCOVA kind of mediates the relationship or mediates the output between the quantile regression and the parametric. So the middle, so if you look at the rank-based ANCOVA in this upper case, you realize that it kind of is centered between the two. So that implies it's relatively more robust if you think about it. And yeah, so I'm just trying to say that using parametric methods expects that you should achieve the parametric assumptions. But if those assumptions are violated, you can use its non-parametric version or try to rather predict the medians rather than trying to predict the means in the presence of departure from these parametric assumptions. And you realize that there will be no much difference. It will still achieve the same goal you wanted to. Yeah. So this is almost the end of our class. So here I've just talked or summarized lots of statistical softwares that are out there that can be used for statistical analysis. But most importantly, there are softwares that you could use to effectively compute sample size. Of course, Stata has very nice functions for that. So we have PS software, you have info and pass especially. And keep in mind that the design of your study can also even influence it, especially those who do clinical trial study. If you are doing a group sequential design, a platform design, and or non-sequential designs, the sample size for the same scenario might vary. Yeah, so this is 9 softwares that can be used to control or to compute sample sizes in different contexts. AMOS is when you are doing structural equation model. Of course, it can be done in R or Python or any other softwares, but it's a customized software for that. So this is actually brings us to the end of our class. So basically what we've learned for this introductory class was not just to see like examples. Next class, we are going to see lots of real life examples because these models are more like customized kind of models that are very imperative across different domains and different fields. But this class was just for us to have an introductory idea into how the nature of the outcome variable or how the nature of variables, the nature of the data structure could inform whether we are going to use fixed effect models or mixed effect models. And by mixed effect models, what we imply, we are still fitting the same fixed effect model, but rather accounting for temporal effect, meaning that anything that introduces some structure to your data, whether the structure is in time or space, we can control for that as a random effect in the model, or whether we want to control for individual heterogeneity, situations where individuals, the outcome, in terms of the outcome, individuals are quite variable, then we can also add patient ID to the model and control for such individual heterogeneity in the data. And then we've also learned about multivariate and univariate methods, and the fact that multivariate methods are able to deal with multiple testing effects, and by so doing have an improved power, and then have a lower false positive or false discovery rate. And then I think we touched a bit on p-values and k-values. I'm sure those who joined later, they didn't see the distinction, but we said that p-values are basically a measure of evidence against the null hypothesis, right? But whilst the k-values is an adjusted p-value in the case of multiple testing. So it means one could still use univariate methods and do multiple testing, but you have to account for or control for the effect of multiple testing by controlling for the false discovery rate and also trying to improve the power. And that is why if you are using p-value without a q-value, then you have to now do something about the alpha level. And by Bonferroni correction, you divide the alpha level by the number of multiple tests. However, if you don't want to do that, you could rather use the k-value instead. Most people are not have probably not heard about the k-value, but it's actually a p-value that has been adjusted for multiple testing, and that is more imperative, especially when you're trying to do multiple testing or multiple hypotheses in most studies, especially in genomics and in proteomics and so on and so forth. So next week we are now going to do so it means this class or this particular session didn't give lots of examples, predominantly because we're just interested in the introductory stuff. But next week, we are going to now talk about these models in the context of specific examples. And then, so we are going to talk about hierarchical regression. Some also call it multi-level regression. But one thing we have to note is that multi-level regression is more of a mixed effect model rather than hierarchical, though it's also hierarchical. So we'll talk about the distinction. People confuse hierarchical regression with multi-level regression. And what about structural equation models? How could it inform the kind of studies we do that we hardly look at it? You realize that all the regression models you've talked about is looking at one-dimensional relationship. What about situations where you want to do multi-dimensional relationship? By one-dimensional in the classical case of linear regression, you are looking at the linear effect or the one-dimensional effect of your predictors on the outcome. But what if you have multiple dependent variables? You don't want to just do multivariate regression, but you also want to identify let's say moderators and mediators in your model, or meaning that some variables might be insignificant in the presence of other variables, or some variables might be significant in the presence of other variables, or there will be a certain third variable that could increase the association between the outcome and the independent. These are some of the things structural equation models seeks to achieve, and we'll talk a bit about that. Time to event analysis, We talk about unstratified versus stratified cases. And remember, in most survival analysis, we are mostly looking at the time to experiencing a certain absorbing event, mostly death, or it could be some other event. But when we are doing that, we ignore the various stages an independent will go through, or an individual will go through before that event eventually occurs. This is to say that if you're looking at, let's say, time to HIV patient dying, okay, that's basically the outcome, right? Would you believe? HIV is not a perfect example. There are certain in logistic case for survival analysis, you realize that we just assume that individual is dead or alive, but someone could be dead but still with the infection. Someone could be dead without the someone could be alive with the infection. Someone could be alive without the infection. And if you don't account for that, how then do we get a more robust model that is useful? Remember, one famous statistician called George Box said, all mathematical models are wrong, but some are useful. It's just to say that how useful your model is will tell its relevance. So that introduces us to something called multi-state Markov modeling that is able to extend the standard survival models, including the standard cost proportional that I'll be touching on next week. It's able to extend that to now look at possible transitions that could occur between some disease states and so on and so forth. And then we'll talk a bit about, and all these, there will be real life examples to back it so that you'll be able to check how it could inform the kind of studies you do. And then functional data analysis, which most people are not aware of, is just another type of analysis where you basically convert your data to set of curves. And those set of curves, we call it functional forms, okay? And with that, if you're looking at rates of change, you can now differentiate your data and still explore the rate of change. I'll give a real life scenario of how I use that to discover a certain important medical finding. So functional data analysis is something that we are going to touch on. And all the methods I've mentioned, we have its functional form. So it means that we could have principal component analysis, functional principal component analysis. We could have functional ANOVA, functional t-test, and so on. So it's just another class of model that literally converts your data from real space to a Hilbert space. By so doing, convert it to a set of curves. So I'll end here, and then there'll be a small service sent by Jenny, and that will just tell how you want future sessions to be done, because this class is quite varying with different people across different backgrounds and different expertise. So that we wouldn't be able to have a particular structure that will suit everyone, but we just want to find an intersection. So and then just to highlight, I also have a YouTube channel where I teach advanced data analysis using R software. And so this slide would also be sent to you or via email, and then